This is a video about trying to build a card for the Music Thing Modular workshop system computer, which does something a bit like the Make Noise MultiMod module. So I'm grateful to Nominalist on the workshop system Discord for pointing out the existence of this module to me. It seems like an interesting module, and something a bit like it might have some interesting uses within the workshop system. So let's just go over quickly what the multimod, roughly speaking, does. I've never actually used a multimod myself. I've looked a bit at the web page, I've watched a couple of videos, but this is my understanding of roughly what's going on. So it's primarily a CV processing system. It has 1 input and 8 outputs, and that input is manipulated in time, and different manipulations of that signal appear on the 8 output jacks. And I think probably the interesting thing about multimod is really the fact that it is a time manipulator rather than a voltage manipulator. So most types of CV processing that we can apply to a signal, something like a wave folder, what those are doing is manipulating the voltage that goes into the module. So if we think of some kind of graph where we've got some voltage signal V as a function of time, and maybe that voltage changes a bit slowly and then jumps up and down a bit or does whatever it's going to do. Most types of CV processing are in the business of altering the voltage on this axis. So we might attenuate or attenuvert that, which would scale or flip that upside down. Or we might apply some nonlinear function like a wave folder to it, which would make a different shape. But fundamentally, we are manipulating the voltage that is happening at the current time. And so a typical manipulator of CV signals would be applying some function f to the voltage at the current time. So we put a signal v of t into it and it returns f of v of t in mathematical notation. Now, the multimod is a bit different because, as far as I can tell, it does not in any way alter this axis, the voltage axis. Instead, all it does is it manipulates the times at which voltages occur. So what this means is that the only voltages that you get out of a multimod seem to be voltages that you have put into the multimod. And so what's happening here is, instead of applying the function to the voltage, what we do is we apply the function to the time. So the output of the multimod is something like v of f of t. Again, to put it in a sort of mathematical function notation. And that's quite an interesting concept, I think, because of course, in a modular system, that voltage can represent any kind of signal. It could be a note pitch as a volt per octave signal. It could be some discrete gates, just 0 to 5 volts. It could be some CV which is representing the volume or the timbre or any other property of the sound. It could be a amplitude which goes into a VCA that controls the amplitude of another CV, so it could be a sort of second order control that affects how much another CV affects something. So lots of different meanings that a single voltage could have. And what that means is that most CV manipulation tools, because they affect that voltage, they have a different effect on all of those signals. So for example, if we multiply a volt per octave pitch signal by a factor of 2, then we completely scale that and make it go out of tune, or we change the set of notes that it represents. Whereas if we scale a set of gates by a factor of 2, the voltage is there. It makes no difference at all. If we do that with a volume CV, it makes it louder. So the same manipulation of that CV has a very different effect depending on what type of signal is going into it. Now, the interesting thing about what multimod does by shifting and manipulating the time is that that has the same effect regardless of what type of signal the voltage is. So I think it's quite an interesting CV manipulation device where you might want to have a single CV control coming in and then controlling different properties of your signal, not just a set of pitches or a set of amplitudes or something, but maybe one pitch, one amplitude, one thing controlling timbre, lots of different sort of musical parameters. And so I think that's an interesting property of multimod. The other thing that I think is nice about it is that because we're manipulating this time axis in a sort of reasonably smooth way, usually, it's not always completely smooth, what we are preserving is the sort of shape of a gesture that comes into the CV input. I think that's quite an interesting idea, where you can input a single sort of gestural shape, be that something rather smooth or rather spiky or random or periodic or so on and so forth, and you can get lots of different variations out of that all at once, feeding different parts of your patch. So it seems like quite a nice way of being able to have essentially one performance control coming in and generating lots of related signals, which can go on to give a kind of coherent patch, where you're not just having to have a single gesture then can control lots of different properties of the sound, but control those in a somewhat coherent way, because the shape of the gesture that you put in is preserved across all of those outputs. At least that's the theory. So let's talk a bit more about what the multimod actually does, or at least what, to my understanding, the multimod actually does, and what algorithm I'm actually going to try and reproduce. So as far as I understand it, at its heart, the multimod is like a big CV tape loop. So I'm going to draw a big circular loop, and we have at one point on this a recording head which records the CV input onto that tape. And I'm going to say that the tape is moving around, let's think, this way. So we've got a big tape loop which is travelling around at some speed, and we are recording data onto it, and so all the data we record gets recorded onto the tape, and so on. And at some point we run out of tape, and our data that we have at this point on the tape, which is old data, is overwritten by what the record head is now recording on the tape. And so that is the CV input. Now my understanding is that the multimod is essentially a set of 8 read heads that exist at certain points on this tape. I'm going to draw 4, in part because it'll make the diagram simpler, and in part because we've only got 4 outputs on the computer, and so we're going to end up doing something which has 4 outputs rather than 8. And so if I just had 4 outputs like this, then this output would receive a delayed copy of what was being sent in. This output would be further delayed. This output would be delayed by even longer, and this output would be delayed by the longest. So with fixed positions for these 4 output heads, we would playback heads on the tape, so to speak. We would have 4 constant delays, so a multi-tap delay system. But what I think is happening in the multimod is 2 things. Firstly, I think these tape heads can move about, and there is a control for the speed, which, as far as I gather, control the relative speed of these heads. So these heads can move around the tape at a certain speed as the tape itself is moving. And the other thing is that you can control the spacing of them. So if they're all moving at different speeds, obviously the spacing of these heads is continuously changing. But if you set it so that they're all moving at the same speed, or they're all not moving at all, then there is a control which allows you to either have them sort of equally spaced out like this, or you might be able to have them all clustered right next to each other like that, or anything in between. So there's a sort of phase control which controls how distant they are from each other when that quantity is not moving. And then the other thing that can be done is we can change the way in which these heads move around. So for example, we could have them overall all moving around, maybe not at the same speed, but all moving around in a clockwise direction. We could have them all moving around in an anti-clockwise direction. We could have them oscillating backwards and forwards, or maybe we couldn't easily do this if it was a physical set of tape heads, but we could have them jump around and select different points at the tape at different times, and so on and so forth. And so the controls that we've got are relating to how we move these tape heads back and forth on this big loop of tape that's going around. As I say, there's sort of three main controllers there that seem to be the different speeds that they go round, how far spaced out apart the sort of phase, and the different modes in which they can move, be it backwards and forwards or going in one direction, and so on and so forth. And then we've got one additional control, which is what is the length of the tape loop. So if we were realising this physically, we would have only one loop of tape, and then possibly we could speed up or slow down the tape itself. Now, in fact, in a digital implementation, that's not quite what we would do, but we've got an additional control on that. So there are lots of other bits and pieces and controls on the multimod, which I'm not going to deal with, at least in this video, things like tempo synchronization and so on and so forth. But for now, I'm just going to have a look at the basics and see what we can get out of the workshop system computer. So let's think about how we might implement this kind of idea digitally. And really for a delay line in a digital system, we've really got two options. I mean, a delay line in a digital system is a buffer of memory, a linear buffer of memory, where we basically store lots of different numbers in a line. And this is our sort of discrete piece of tape that's split up into discrete numbers, and we can save numbers onto that with our record head, and we can read numbers back out of that with our playback heads, and then we'll loop. When we sort of move off the end of our loop here, we'll loop back on here to simulate a loop of tape, a closed loop of tape. Now, there are sort of two ways of doing a buffer like this. If you've got a fixed length of buffer, that's very easy. You just choose your sample rate for your audio system and you make the buffer an appropriate multiple of that, and that's the length of your buffer. If, as in this case, we want to have a control that varies the length of the buffer, and that can happen while the card is running, then we've got a couple of options. And these have sort of direct analogues in a physical tape system. We can either speed up and slow down the tape, and if we speed up the tape, then the amount of time it will take for sort of the duration of the tape loop will reduce because we get to the end more quickly. And that's certainly the way you would choose if you had a physical tape here. In the digital system, actually, that turns out to be a little bit tricky, because really in a digital system, what we want to do is record each sample of our digital to analog converter, our analog to digital converter, our inputs. We want to record each sample on a new space in our buffer. And if we're moving the buffer at a speed which doesn't line up with our sample rate because we've sped it up or slowed it down, that then gets a bit awkward because our samples then sort of may no longer lie on our tape. We might have multiple samples within some cells and some cells without any samples, and so on and so forth. So it turns out that the easier thing to do digitally is to keep the tape running at the same speed but change its length. And so the way of thinking of this is that we've actually got a really, really long piece of tape, and we have our tape loop like this, but actually our tape loop is just part of a much, much longer piece of tape which goes off and sort of coils up in the distance or something, and we've just sort of sellotaped it together here, and our system is just using this little bit of tape here, and potentially then if we want to expand the length of this tape in order to lengthen the buffer, all we do is we untape it here and reconnect it further down the tape, and we get a longer longer piece of tape to deal with. So obviously pretty impractical to do that physically, but that's the easier thing to do in a digital system, because you just end up recording at the same speed all the time. The tape's always moving at the same speed through the record head, so you always record 1 point per sample, but all you do is say that at some particular point you declare that to be the end of the tape, and that's the point at which you loop round and start at the beginning. And this point at which we declare as the end of the tape, we can move back and forth to lengthen and shorten the tape. So that does have a slightly different sound to it when we change the length to it than speeding up and slowing down the tape, but at least for this video, that's what I'm going to do. And so let's sort of think about what the ingredients of this system really are. We've basically got two aspects of it. We need to implement some kind of system where we implement the record head, where we record to a tape, and that tape loops round and round, and we can change the length of the tape and so on and so forth. And we can implement that bit. And then we've also got these recording heads where we can pick up signals at particular points in the buffer, and we need to implement some way of moving these backwards and forwards around the tape in the sort of sensible way. Now, the other thing that MultiMod does, which I haven't mentioned yet, is it does work even if you don't provide an input signal. So there is a normalization on the input jack, and it's not completely clear to me what that normalization does, but I think that it essentially records where you are in the tape loop, and that information about where you are in the tape loop is the normalization signal. So if you don't have an input into the signal input here, it looks like what happens is that the position in the tape, the sort of the angle around which you are, becomes the signal. And so what that means is that if your heads are just moving through the tape, you end up with a sawtooth wave because your angle increases as you go around, as the angle increases you go around, and then resets back to zero, back to a negative value as you go through the tape head. And so we should be able to implement that as well. So let's actually go and try and implement some of these things in code. And what I've got here is a simple computer card piece of code. I've just set it up with a simple Raspberry Pi Pico SDK project here. So just got that in a terminal. I've just got a simple CMake file which I will include with this project, which sets that up. And to test, all I've done is just made a standard computer card class. So this is called CVMod. That's what I'm going to call our project. And for now, all I'm doing in that is just setting the audio output 1 to the main knob value, audio output 2 to the X knob value, CV output 1 to the Y knob value, and CV output 2 to the switch value. And the reason I'm doing this is because I want to test the 4 outputs which we're going to have on the computer card version of this module. I'm going to, at the moment, I'm visualizing those with an oscilloscope. And so with this program loaded in onto the computer, I should be able to turn the main knob, and we see that the top line here moves. So this is my audio output 1. I turn knob X and we get a signal on audio output 2. Turn knob Y and we get a signal on CV output 1, and flick the switch and we get a signal on CV output 2. So that's really just checking that my scope here is giving me the right signals. So I think probably for this project, having sort of live visualization of the 4 outputs of the module is going to be pretty important, and maybe more important than having a debugger set up. So for the moment, I'm just using standard copying to the computer card via the USB port. I'm not using the Pi Pico debugger, and hopefully that will be enough. We will see. So as I say, we've just got these 4 lines of test code, which are just to help show that I've plugged this into the right scope channels. And I've got a simple setup here. I'm setting the clock to 192 megahertz, just because why not for the minute? We may as well get this is a slight overclock to the original specification, but that should be fine and means we are less likely to run out of processing power and have to do some optimization. And then I've got just the code just to make a new instance of this class, enable a normalization probe, which we're going to need as mentioned, and run that. So, as I say, there were 2 main bits of software that needs to be written. We need to write something to do with this tape loop and recording to that, and then we need to write the reading from it with the read heads. And so let's start just by making a buffer for recording. And it's going to have a maximum size for that, max loop size. And we need to think about how big can our buffer be. So we've got over the order of 250 kilobytes of RAM on the Pico, of which I might want to use maybe 200 kilobytes for this to leave a decent amount of space for other bits and pieces. And because we have 12-bit recording, I think I'm not going to here try and pack 12-bit signals. I think I'm going to expand them to 16-bit, accept the extra memory that takes just for simplicity. And so we'll be looking at 2 byte values within our buffer, and we can have about 200 kilobytes, so that gives us somewhere around 100,000, I'm going to say 96,000 different entries in our buffer, and let's actually make that buffer. So I'm going to make this out of signed integers. And given I have to find this buffer, I should make a constructor to do some setup. And one of the things I want to set up is just to null out that buffer, just to make sure that we don't have any data in it initially. Okay, so that's what we've got for the buffer. What we then need is some way to store how long the loop that we're actually selecting is. So if we go back to our description here, we've got this buffer which is our entire length of tape. We actually need how much of it is in the current loop. So I'm going to want something, say loop size. I'm going to store this as an unsigned, and we're also going to want something which indicates where the recording head is on that loop. So I'm going to call that one loop index. Okay, so we need to do something to set the size of the loop, and we need to do something with the loop index. So fundamentally, for the moment, I'm just going to leave this old code down here. Fundamentally, what we're going to want is some code a bit like loop index ++, and if loop index is greater than or equal to loop size, loop index is equal to 0. So that will increase our loop index and reset it when it gets to the loop size. I guess something to think about at this point is how long a recording we actually want and what sample rate we really want from our recording. So this is a CV processing module, and in particular, because we're using the CV outputs, which have got low pass filters on them, we're not going to be able to kind of do hi-fi audio with this, at least not through the 2 CV outputs. And so there's no particular point in doing everything at the sample rate of process sample, which is 48 kilohertz, with computer card, we can reduce that down by quite a bit. And I reckon that we can probably do that by a factor of 4. So let's say 12 kilohertz. So what I'm going to do is make some new variable called sample count. And sample count is going to be something which just counts through 1 through 4, and if it's equal to 4, we reset it. And if it's not equal to 4, we're actually going to return from process sample immediately. So what this is doing is we only process samples at 12 kilohertz, discard 3 out of the 4 samples. And so what that means is from this point on, called at 12 kilohertz. So 12 kilohertz, 96,000 samples gives us 8 seconds of recording, which isn't too bad. I think it's somewhat shorter than what the multimod allows, but that's not too bad. Okay, so the next thing we need to do is think about how to set the loop size. And so I want to have this set by a knob and probably some CV in due course. Let's think about what that might actually entail. So we need to set the loop size, and I think the loop size should probably be an exponential function of some knob position. So I'm going to create something called time knob, which is going to be, let's just make this equal to knob val x. Let's have the x knob control the time. And what I want to do is set the loop size is equal to some kind of exponential of time knob, because with times like this you really want kind of smooth control over a whole range of times from, I guess, up to 8 seconds we said is the maximum at the moment, but down to 100 milliseconds or something maybe like that for much faster loops. And so the question then is, how can we do exponentials? We could use floating point processing. That's relatively slow, and so I'd like to avoid that if I can. And so what I think I'll do is something that I did in utility pair, which is to create a lookup table of exponential values, and then I can use those wherever I need an exponential in this program. And this gets a little bit involved, but I think it's worth going over, and I'll put some chapters in the video so you can skip to the next chapter if you're not too interested in how to do this. So this is pretty similar to some stuff I did in utility pair. So I think when we are making a lookup table for exponentials, there are kind of various conflicting priorities. We could have a huge lookup table, but in particular for this module, one of the things we really want is to use as much memory as possible for the buffer for the recording, so we can get as long a recording as possible. So I don't really want really long lookup tables. And so what I would rather do is generate a shorter lookup table and interpolate between those entries linearly. That linear interpolation should be good enough for this purpose when this isn't directly controlling pitch or anything. And that will allow me to have relatively few entries in the lookup table. And the other thing is that if instead of an exponential to the base e, if I do a powers of 2, that's quite a convenient format because I only need to generate 1 octave of that table, because we can very efficiently divide by 2 using bit shifts. And so what I want to do is create a function pow2 and this is going to return 2 2 to the power of the input divided by some number. So we're going to have some number of integer indices per octave in our lookup table, and it doesn't really matter how many we choose. I think I'm going to want this to cover, as many powers of 2 as I reasonably can. I think a reasonable resolution is going to be something like 4096. Again, just choosing a nice power of 2. Everything's going to be in powers of 2 because there's going to be a bit of binary manipulation here. So what we want is to return 2 to the power of in over 4096, and this is going to be the integer part of this, and it's going to be approximate because we're going to be doing some lookup. And so what we're going to do here is there's sort of 3 steps of this. I think we've got octaves, we've got lookup table, and we've got an interpolation between the lookup table. And so I think for those 4096 steps, I think what we're going to have is a 7-bit lookup table that is 128 entries, which is not too many, with 5 bits, that is 32-step linear interpolation between steps. And I found that works reasonably well. And then we can have an index for the octave as well above that. So each lookup table is only going to cover a single sort of power of 2, going from a number to nearly double that number. So let's make that lookup table for the powers of 2. Power 2 128, and that's going to have 128 items. And this is another thing that we will deal with in the constructor. One of the nice things about the RP2040 is that even though the floating point stuff is a little bit slow compared to the integer, you do have it available, and that means that rather than generating lookup tables using some pre-calculated numbers from Python or something which I just paste in the code, we can generate it live in the constructor. So what do we need to do? I want to set f to some power of 2. Not quite sure which one it's going to be yet, and then I'm going to have to put a semicolon there to stop it from... Not quite sure what that is going to be yet. I'm going to fill out my lookup table, and I'm going to set the entry to this number, floating point number f, and then what I'm going to do is multiply f by whatever the 128th root of 2 is. So let's get out a calculator. Okay, so 128th root of 2 is that number, which will represent as a floating point 2 to the... And so what we're doing is, in our lookup table, we're multiplying f by this constant fraction each time and going up 128 times. So that means that once we get, we start our lookup table with some power of 2, and then as we go through 128 entries of this lookup table, we are going to multiply that by a factor such that by the end of the lookup table, it's very nearly doubled our number. And if we took one additional step, it would be exactly doubled. And so that's our lookup table, is then describing a single sort of doubling of this function. So the question is what power of 2 we actually choose, and this gets a little tricky because we need some headroom for the linear interpolation that we're going to do in this function. So I think probably the best thing to do is to write our function here, and then we'll see what power of 2 should actually go here. I'll explain what I mean as we do that. So, from our input signal, we've said that it's the integer part of 2 to the in over 4096. So 4096 is 2 to the 12, and so in a sense the octave is whatever input number is bit shifted down by 12 bits. So this is just in divided by 4096, but the floor of that, the integer part of that. And so that's going to be our octave multiplier, and what I'm going to do at the end is bit shift the answer that I get down depending by some power of 2 depending on what that octave is. I'm then going to need caps lock on a index into my table. So this is going to be in, and I've got to select the right bits. So what I want to select is a total of 7 bits, not including the 5 bits at the end of the number. So that is going to be 0 times FE, and I want to shift that down by 5 bits. So OXFE is equal to 1, 2, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5 in binary. So that picks out those 7 bits and shifts them down to give the index. Oh, we need to actually call this something. This is going to be index, but it'll actually be the first of 2 indices because we're going to do some linear interpolation. And let's actually just look up the value at that index. So as I say, we're going to do, so this is sort of table index and the value of the lookup at this point. We then need a second index because we're going to do linear interpolation between them. So this is int1 plus 1, and I want to make sure that that wraps at 128, so I'm going to bitwise and with 7f, which is all the bits, 7 bits turned on at the end of the number, and val2 is power to 128, our table that we're going to generate. Now, there's a slight trick here, which is when we are actually, if val2 is actually equal to 0, which is when ind1 was the last entry in the lookup table, really, rather than look up this power, this number here, really what we want to be looking at is the next octave in our table. So we're kind of cheating by only having 128 elements in our lookup table. We should have 128 elements for each octave of our power of 2 function. But to save some memory, I'm not doing that. But what that means is if val2 is coming from the first element, so if ind2 is equal to 0, really rather than the first element of the current octave, it should be the first element of the next octave. And so we need to double val2 in that case. So we're interpolating between end of one octave and the start of another. Okay, and now we've got our lookup table values val1 and val2. We can do our interpolation, which I said was going to be 5 bit, so 32-step linear interpolation. And so what we want here is uint2t subsample, where we just want the last 5 bits of the input index, so that's our final 5 bits. And we then want to have our interpolated value, which is val1 times 32 minus subsample plus val2 times subsample. So standard linear interpolation. And now I need to shift this down depending on whatever octave we are actually in. And here's where we need to think a little bit about what numbers are actually going to go in this table. So now is probably the time to turn back to this line, which we didn't actually write, because what we need to think about is what is the maximum element in our table, because we need to make sure that this operation in particular doesn't wrap. And so we have unsigned 32-bit integers is what we're dealing with. So we've got 32 bits to play with. We are multiplying by numbers up to 5 bits here in these two, and then we're summing two of them together. And so we can really have 32 bits minus 5 because we're multiplying a 5-unit number, minus 1 because we're adding two of them together. So 32 minus 6 is going to give us 26. And so I think the largest number, actually no, we don't need to account for, because we're multiplying, because we're adding something 32 times minus subsample and subsample, we don't need to account for the fact we're adding two together. Okay, so what we need to do is, it's just the largest number in our lookup table is allowed to be just shy of 2 to the 27. So the first number in lookup table has got to be 2 to the 26. And so we want to calculate 2 to the 26, and that is 61708864. So this isn't some power of 2, this is 2 to the 26. And so we now need to think about what we shift our value down by to get the right octave. And in fact, because I'm going to be returning a value here, let's just have a think. The question is, what value of let's have a think. So it's going to be something minus the octave. And so maybe the easiest way of doing this is to say that we know that pow2 of 0 should equal 1, because 2 to the 0 is equal to 1. And so in that case, subsample is 0, and we're just taking the first element. Okay, so that's just giving us 32 times, okay, it's giving us 5 bits times that, so we just need the 26 from our lookup table plus the 5 gives us the 31. So I think that should be right. So I think that pow2 function is now going to give us the integer part, roughly speaking, because we are using linear interpolation, so it's not going to work, it's not going to be absolutely precise, but it should give us the integer part of 2 to the in over 4096. So that is a function which should hopefully give us an exponential function. Let's actually just make this and see where I have made any errors. Okay, sample count needs capitalization. Okay. Okay, good. This is not actually going to affect the output at all here, so I won't bother copying it over to the pi yet. Okay, done with the calculator for the minute. So let's have a think what we were doing, why we were doing this in the first place. Oh, that's interesting. Compiled even with that. That's not quite what I wanted to do. But we want to set the loop size to some kind of exponential of the time knob. Now, let's think then about what the maximum loop size we can have. So we want the maximum loop size should be less than 96000, because that's what we set as the size of our buffer originally. So we don't want our exponential function to be going much above that. I think just for safety I will say if loop size greater than or equal to max loop size equals max loop size -1, just so that if we end up getting this wrong we don't overrun our buffer. And so I'm going to say this wants to be power of 2, and it's going to be something plus, it can be something of the form a plus time knob times b, where b is going to set, so time knob has a range, okay, time knob has a range of 4096 because it's coming from the 12-bit knob values, and so if b was 1, if we just had this, then the time knob would change the power 2 input by 496. That would change the output by a factor of 2, and so in this code here, b just sets the number of octaves in a rhythmic sense, the number of powers of 2 between the maximum and minimum loop size that we can have. So the question is, what we know roughly what the maximum loop size should be. We want it to be 96,000, which we said was 8 seconds. And how small do we want the minimum to be? Somewhere around 1/10 of a second, something like that. So that means probably we want 7 for B, because that means we get 8 seconds. 8 seconds over 128, which is 62.5 milliseconds. That's about right. So let's say minimum loop size should be about 62.5 milliseconds. So now we need to set this A value, and what I want for that A value is that when time knob is at its maximum, I want that power of 2 to be about or just under 96,000. So what I want is log 2 96,000 multiplied by 4096 minus 7 times the maximum value of time knob, which is 4095, I think, and this gives me 39126 point something, but I'm gonna give it 39125 because I want to make sure I don't actually, oh yeah, no, I want 39125 because I don't really want log 96,000. I want it to be 95999 because that's the last index of something actually in the buffer. Fine, so I'll subtract 1, give it 39125. So that in principle should never go over the maximum loop size. Okay, so let's actually do something which might test how this code is working. And we haven't really got much set up yet, but what I'm going to do, I think, is just flash an LED every time the loop gets back to the same place on the tape. And even though we haven't really implemented the tape yet in any real way, that should tell us a little bit about what's going on. So this is another trick from utility pair that I quite like. How do you flash an LED briefly, or indeed I use the same thing for generating short trigger pulses. I have some counter, so I'll have int pulse flash counter, and that starts at 0. And when I want to make the LED flash, in this case, I set it to some number, which is the number of samples that I want it to flash for. So that's 200 at 12 kilohertz. So that'll be a very brief flash. And then at the end of my function, if pulse flash counter is greater than 0, then we turn on an LED. Let's have the bottom right LED and pulse flash counter minus minus. So if it's greater than 0, we subtract something from the pulse flash counter, and if it is already 0, we don't subtract anything, but instead we turn the LED off. And so hopefully, let's have a look. We've got a loop size set up. It's connected to the knob X. We've set it to an exponential. We have a maximum loop size. We're increasing the loop index. When the loop gets over the loop size, we reset it to 0 and we start our flash, and this should process that flash and turn the LED off after 200. So let's try making that counter. I can't spell. Right, let's see what's going on there. Any sign of life? Yes, we have a flashing LED. I don't know if that's actually visible. Yes, it is visible. So hopefully when we turn this down, that's maybe a little difficult to see on the video, but that seems to be flashing about right. And if I turn it to the maximum value, we should have flashes about once every 8 seconds. Excellent. And that looks almost solidly on in the video, but I can just about see in real life that that's flashing what looks plausibly a bit like 62 milliseconds. Good. Okay, so it looks like we've got our length of tape loop sorted for now. We now actually need to record something onto the tape loop, and I think actually that's probably not too difficult at this point. I think all we need to do is just say could it be as simple as that? Buffer loop index equals audio in 1. So I'm not actually dealing with the normalization at the moment. Maybe I'll do that. So I'll set up a recorded value. If we actually have a jack connected into audio 1, then recorded value is equal to audio in 1, else. And now here we said that it was going to be something to do with the kind of the phase of the recorded position on the tape, and that needs to change to recorded value. We haven't really worked out how to do that phase yet, so at the moment we'll just record 0 if nothing is connected to the audio. But that should now be recording onto the tape. Now, of course, we don't actually have a way of playing data out of the tape yet, so that's not so useful. But in principle now we are recording onto the tape. Okay, let's now think about how we're going to describe the position of the playback heads on our tape loop, so to speak, and also the position of the recording head, which I said was associated with this normalized, the normaled value here. So let's move back to the sketch for the moment. So I think the thing to think about maybe is that actually when we're dealing with a linear buffer like this in a computer, we don't have a moving tape loop. Instead, the recording moves along at a particular speed. And so the way to think of this is we've got our big loop of tape like this, and we've actually now got our record head moving around it at some speed, and that speed will always be speed 1 in a sense, because we're always, at each new sample, we're always putting it at the next discrete sampling point on our tape, and so we move through one of those each sample. And so these sampling points, we start with the numbered 0, 1, 2, and so on and so forth, and we go around to in our loop anything up to 95,999, and we go back to 0. And then once we get round to the maximum, we then want to return back to 0 again. And so we have this going on, but we've also got our 4 tape heads that are in some positions, maybe not equally spaced, maybe equally spaced, whatever it might be. And these are all moving around back and forth as well. And in particular, they're moving past, I guess, what you could regard as the sort of 0 angle on this. That's not a very good line. Let's draw it from this way. The sort of 0 angle, they reach sort of 360 degrees here, and then they go back to 0. And this is always a bit awkward in coding when you have things which, when they reach past the end of something, have to loop back to the beginning of it. We're going to end up with lots of statements about if something is greater than the limit, then we set it back to the beginning, and so on and so forth. And the other thing is that we want to be able to calculate the relative angles between some of these things. So in particular, when these record heads are also moving with the playback buffer at the same speed, one of the things that we're going to be able to control, or we're going to want to control, is the angles between these. So we want to control kind of how far ahead or behind of the record head are each of these playback heads. And that gets really fiddly to do when you've got a kind of circular system like this, because, say, this record head is actually some way behind this playback head is somewhere behind the recording head, but actually the angle of this is larger because we've started, the record head is now at angle 1, it's just got past the first element of our buffer, but this is going to be, even though it's behind it, will be at a much larger value, and that's because we've wrapped around through 0. So doing that kind of arithmetic is basically a bit of a pain in coding, unless you can exploit one of the nice properties of particularly unsigned integers in C and C++, and that is that when you've got a uint 32t, an unsigned 32-bit integer, in C and C++, manipulation of that number, that is not really the integers, that is the integers modulus 2 to the 32, which means if you take this numbering going around the tape loop, and you set up a numbering system where that goes from 0 all the way up to the last point here, which is 2 to the 32 minus 1, which is 4 billion and something, then these unsigned integers in particular are guaranteed to loop around in exactly the way you expect. Integers modulus a number is exactly the way that you would represent discrete points going around a circle that loop seamlessly back on again. And so in particular, if you add together two uint32t's such that their sum is greater than 2 to the 32 minus 1, it will wrap around, they will wrap around in exactly the appropriate way and end up at the right point. So the long and short of it is that these numbers are really convenient for representing angles around a circle like this, so that you don't have to do any of the checking of going over the endpoints yourself. And so what we have then in our system is sort of two different measures of how far we are through the tape. We've got actually how many samples in our buffer, which goes from 0 up to some number, but that number is at most something around 96,000. But I think we also actually want to do the manipulation of where these playback heads are in this unsigned integer space going all the way up to 2 to the 32 minus 1, and then we'll convert it back into the smaller numbers used for the actual samples on the tape later on. So let's have a look at how we might do this. And I guess the thing to think about now is that here the record head is moving around similar, just as the read heads are as well. So let's go back to our code and turn on the computer camera, and let's have a look at how we're going to do this. So I think I'm going to call those numbers that go up to 2 to the 32 or thereabouts, I'm going to call those a phase, I think. And so something I want in my class is the position of the recording head, and I'll call it record phase. And what I want this to do is, this is going to essentially be representing the same quantity as loop index, except loop index goes from 0 up to whatever the current length of our loop is, and the what did I call it? The record phase is going to go up to 2 to the 32. So let's have a look at how we set that and where we are going to do that. I want to do it after I've set the loop index here, but before I might need to use it in the recorded value here. So record phase is loop index times some number, and what that number is going to be is okay, I can't exactly represent it. I want 2 to 32, that's actually 2 to 32 minus 1, but that is going to be close enough, an error of 1 part in a few billion. And I want to divide it by loop size. Okay, so that means that as loop index goes from 0 to loop size minus 1, record phase goes from 0 to something approaching 2 to the 32. In fact, I think probably what I will do is save that number as something called a loop increment, because I think we're going to need it again when we come to convert the phases back into the positions in the buffer. So that's times loop increment. Okay, good. So now the recorded value that I want to save is actually going to be the record phase, which is exactly what my comment from earlier said it was going to be, the phase of the recorded head position. But it can't be exactly that, because this is we need to convert it from 32-bit unsigned to, let's make this the same as audio 1 in, so that's signed 12-bit. So that means we're going to have to shift it down by 20 bits and subtract 2048 to convert it into a signed value. Okay, so this should mean that when we have a jack connected, we record audio in 1. When we don't, what we will record now is, just to go back here, is the position of this red record head on the stationary tape as it goes round. So that will increase from something negative, increase in a kind of ramp wave, and then drop down again at the end. Okay, so we've got that phase, and I think we can then use that phase to actually get some outputs from this. So we can start doing something finally with these green recording arrows, or sorry, green playback arrows, I should say. So what can we do with those? And I think this is something where I want to, we've written quite a lot of code and haven't really tested any of it so far, other than checking that we've got the light blinking at some speed. So what I think I want to do is just start with a relatively simple bit of, okay, let's start with something really simple, which is where I just try to read back exactly the value that I have just written into the buffer. So we can finally get rid of those, and I'm going to need some way of reading from a buffer. From some position. Okay, so how are we going to read from buffer at some position? Well, we could just specify the index of the buffer, so we could just say like buffer index or something like that. What I think I want to do, because we're going to be potentially slowing down, we're definitely going to be playing signals at rates that are not exactly the same as the rate they're being recorded. I want some kind of, again, linear interpolations. In fact, I'm going to, don't know quite what I'm going to put in there yet, but I'm going to be reading from the buffer. So I am going to need to write another function now to read a signal from the buffer. In 32T, I could use in 16T to be honest, but it doesn't really matter. So this is reading from the kind of the tape loop, and I'm going to read it at some position, and in fact that position is going to have some of the bits here. It's a bit like the pow2 function. The low order bits I'm going to have as linear interpolation, and the high order bits are going to be sample index. Now the sample index needs to go up to 96,000, which is more than 16-bit. So let's give it 24 bits of high, 24 bits of position R sample index, low 8 bits, because we've got a 32-bit position R sub sample, which is 8-bit linear interpolation. Should be okay. So in fact the code here is going to be basically a simpler version of the POW2. This is the sort of subsample, and it's FF this time because we've got an 8-bit index, and now we can just shift the position down by 8, and that gives us our sample index. And as we did before, we need to look at what happens at the end of the buffer when we're linear interpolating. So the next sample is the sample plus 1, but if that one is actually bigger than the it's not going to be max loop size, it's just going to be loop size, which is the size of the buffer that we're currently using. Then okay, that should be fine. In fact, in this case, we could just set it to 0, but subtracting loop size is the same deal. And so now we just need to return, and it's just the usual linear interpolation buffer position times 256 minus r plus buffer position 2 times r. And in the power 2 case, we then did a shift down by 5 implicitly in this. Here we haven't got this octave stuff, so we're going to need to shift down by the 8 bits of our multipliers here, and that should give us a linearly interpolated read into the buffer at any position. Okay, so what positions do we actually want to read from the buffer? Well, that's the question that we have here. And I think really what we want to do is let's think. Essentially, we want to take the phase of the let's just make a temporary variable read phase. Eventually we'll have 4 of these, but I just want to test that something works here. So I'm going to set the read phase is equal to the record phase, but what I'm going to do is subtract some number, and let's subtract half a buffer's worth. So what we're going to have is just in this temporary test, we will have the buffer here, and exactly half a buffer away we'll have a temporary record head there, just recording what's being played back. Sorry, we'll have a temporary playback head playing back what is being recorded, I should say. So let's subtract, in these phases we go up to 2 to 32, so half of that is 80. That's 2 to the 31. And then I want to convert that phase back into a position in the buffer. And so how am I going to do that? I guess I need to multiply whatever we get read buffer position is going to be equal to. Okay, so in order to convert from a buffer position into a phase, we multiply by the loop increment. Now we need to convert back the other way. We need to multiply by our read phase by the loop size, and I can see we're going to run into some problems here, and then we need to shift it down by 32 to get the buffer position. But actually we don't shift it down, so there's 2 things wrong here. We don't shift it down by 32 because our read buffer function, actually we said that the bottom 8 bits were subsample and the high 24 bits are sample index, so we need to multiply any input to that by 256, or equivalently we don't divide down by quite as much here. And then the second thing is this is definitely going to overrun a 32-bit integer, and that's because read phase already uses up to all of the 32 bits of the integer. So we multiply by loop size, we're definitely going to run into problems there. And so I don't love it, but I'm going to promote that to a 64-bit integer and then do a multiply on that. So 64-bit integer multiplies are not particularly fast, but they are better than floating point multiplies. But I think we're only going to end up with 4 of them in this system, which is probably doable. I mean, one thing to say about performance is that at the moment we're throwing away a lot of performance because we're discarding 3 out of every 4 samples, but because of the way that computer card works, we don't get that time to execute the sample where we're doing all the work. So really, we're trying to do all of this in one 48 kilohertz sample, but we're really only processing the samples in a meaningful way at 12 kilohertz. So if we do end up with performance problems, we can, by utilizing the second core, get around this and have the full 1/12 kilohertz to do this work. But we'll see if there are problems before we go there. Okay, so audio out 1 ReadBuffer pause. In fact, what I'm going to do is set that, just for testing for the moment, I'm going to set audio out 2 to what we're reading, and I'm going to set audio out 1 to audio, what did I call it? I won't do audio in 1, I'll do what we are recording onto the tape, which we called recorded value. So audio out 1, which is the yellow line here, is just actually recording what we that's literally just what we are sending in through the audio in 1, or the normal signal that's going into there, and audio out 2 is going to be what is being read from that. So let's see how we're getting on. Okay. And it compiled. Let's copy that over and see what we get. Okay, we have some signals and they look broadly promising. So let's turn down, and that's speeding up. Ooh, interesting. Okay, so something I can see already is as I change the so actually this does look quite promising, because it looks like if I just leave the knob stationary for time, it does look like the input, which is the yellow signal, in fact this is the normal. Okay, so there's lots of things that are working quite nicely here. Let's just go through them. We don't have anything plugged into the audio input here, so the recorded value is being set to the record phase, and I'm converting that into the full signed 12-bit value. And that is indeed doing what I was hoping, which is a ramp wave going up from -6 volts to +6 volts, which is basically the output range of this. So we're getting what we wanted from that phase and converting it. Now the other thing that's working quite nicely at the moment is that this audio output 2 is reading from the buffer. It does appear to be reading half a cycle delayed from the recorded value, which is what I wanted, and it does appear to be displaying the same signal. So that much looks good. If we turn the signal to something, interesting. Okay, we're getting quite a lot of mess there, but if we just let it settle down and record a full loop of the tape, at the longest duration it's doing the same thing, it's just taking ages, and at the shortest duration, you can't really see it. This let's just turn this up a bit. Yeah, okay, the shortest duration it's doing the same thing as well, roughly speaking. Okay, so that much is working well. Let's check. So one thing that is not immediately clear from this is whether this is, it's offset by 180 degrees. So that's a little bit tricky to see whether it's sort of going ahead or behind. So what I want to do, I think, is control this quantity here with a knob, and let's make that. So I think I want the speed control to be the main knob, and so the knob I've got left is the Y knob. I'll call this phase knob is equal to knob val Y, and this then, so that is 2 to the 31, and I instead want to make this knob val, what did I call it, phase knob times, so phase knob is 12-bit, I want to multiply it up to be 31 bits, so I want 2 to the 19, 524288 apparently. So I think if I multiply that by 524288, then the knob Y will control the phase shift. Let's have a look. What's knob Y set to? Okay, if we set knob Y to 0, okay, that's nice. So knob Y is 0, we have no phase shift. Ah, that's interesting. Okay, so that. Oh no, that is right. Right. Okay, so yeah. So as I increase the knob Y, the blue signal is delayed from the yellow one. Initially, I thought it was in advance of the yellow one, but that's because my brain was thinking in terms of a normal oscilloscope rather than this in roll mode. And in roll mode, you can see that it being shifted to the right, the blue signal being shifted to the right is the delay. If I turn that all the way, we should get we should get 180 degrees out of phase now. Good, okay, so that is controlling the phase. So that's fair enough. And that knob, actually, if I turn it back and forth, it's sort of reasonably smooth. Okay, as you go over the boundary where the signal jumps, that is reasonably smooth. Something which wasn't reasonably smooth before, yeah, okay. So actually it's a bit of a mess when you're, if I sort of mess about with the duration knob, then you get all sorts of weird stuff on the signal before you sort of have to have a full loop. Yeah, okay. So it's a bit messy when you're changing the length of that. So we'll have to deal with that at some point. So what's going on there, I think, is let's just turn that off. What's going on is if we go back to our kind of picture of the tape as a tape loop, but actually rather than it's actually a buffer where a bit of it is allocated just the loop and all the rest of the tape is kind of just hanging on to the tape. When we increase the length of the tape loop by a bit, what we are doing is introducing into the tape loop a new bit of tape, which is sort of this bit here. So if we increase our tape loop by a bit, we'll pull in a little bit of tape, which wasn't previously in the tape loop, but now is. And that colour is not terribly visible. This little bit of tape here. And that little bit of tape, who knows what is written on that bit of tape? If we've been playing around with a fixed length of loop for a while, whatever data is written on that tape, if any, is probably from a very long time ago. So we've basically got all sorts of nonsense from different plays of the tape and different times the loop was a given length, all kind of jammed into the onto the tape here, so it's a bit messy. And then that tape, when we lengthen our tape loop to include that tape, it ends up on the tape loop, potentially goes past one of these playback heads before it gets erased by the record head. And so what we're getting with the noise is I think that going on. So we'll have to think of a way to fix that. But actually, for now, what we haven't yet tested is just how this works with a real signal, because I haven't put anything into the audio input yet. So hopefully, I mean, all we've set up here is a simple delay loop where we're just delaying the input signal by some amount. So if I plug in, find a long enough cable, if I plug in, let's use the slopes. I'm going to plug the slopes into the input, okay, and we get nothing. And now if I do a blip, yeah, perfect. Do a blip on the, I say perfect. What was that little glitch? Ooh, interesting. Okay, so there's a tiny little glitch there as well. So, I mean, broadly speaking, this is looking interesting. Oh, right, okay, so broadly speaking, he says this is looking quite good in the sense that, and I'm going to increase there. So this is some of this noise that we're seeing on the output. As I change the delay loop, I just lengthened the tape. We send a signal in, and a signal comes out sometime later. Great, but when so I guess here actually we're recording a lot of data on it, but when you get all sorts of mess when you change the length of the loop. Now you also actually get we also saw some glitches. I haven't seen one in a while, but we saw some little spike glitches on the output, and I suspect that might actually be caused by the same. Let's turn this into some kind of triangle wave and see whether we can see anything. So I suspect that let's try and turn this down, see if we get any. Yeah, we do. Okay, so I think what's happening with these just occasional spiky glitches that are happening, I think probably okay, so what we can see is most of these glitches are taking us to the full 6 volt amplitude. There's one. Let's see if there are any more. Not all of them. That one's below the full 6 volts. But I think what's happening here is actually it's part of the same problem I was talking about before with mess on the tape loop here, and that is the knob values that you read from the computer card are not completely smooth, so it's quite difficult to get 12-bit precision out of the analog to digital converters on the computer, even if you do a certain amount of filtering, which computer card is doing. It's not bad, but they will be jumping up and down by 1 or 2 values. And I think what's happening here is that we are occasionally jumping up by a little bit, lengthening our tape by a little bit, putting a little bit of random data, and that data is something which we previously recorded, which is why the output signal, the spikes we're getting, are kind of look like they could well be previous values of the recorded signal. I'm not explaining that terribly well, but the proof of the pudding will be whether we can fix it by adding a load of hysteresis onto the time knob so that we don't get jittering. So in order to do that, what we need to do is move time knob so that it becomes a variable that persists in between samples, and we'll set it to 0 at the start. And then, where are we? Okay, so what we want to do here is basically something like if knob val x is greater than time knob plus some threshold. I think that 15 is pretty aggressive, but I think I'll definitely fix the problem. We can probably be a bit smaller with that, but let's just see whether it fixes it first. So basically, if the knob value that we've just read is more than 15 away from the current value of our knob position, then we set time knob is knob val x, and this is loop time knob x has heavy hysteresis to avoid glitching. Okay, so this won't fix the issues when we make a really big change on the time knob. That we'll have to deal with some other way, but hopefully that will fix knocking cables everywhere. Let's see if we get any glitches. The trouble with glitches is you never quite know. That does look promising. Let's turn it down actually to a very short time base. Okay, so I got glitches when I was moving the knob, which is not surprising. Okay, yeah, that looks as though it was probably it. I'll go over to a really long time base now. Okay, good. No obvious glitching. Right, so I think that was just hysteresis. So this is one of the kind of interesting things about working on an embedded platform rather than on like a desktop plugin or something, is that all the time on an embedded platform, all of the controls that are coming from an ADC are quite likely wiggling around slightly, and that can be quite different can make things sound quite different. In fact, the Reverb Plus card sounds a lot better with a certain amount of that going on, which I guess was true of the original Lexicon algorithm. The Lexicon hardware as well, I guess, had a similar thing. On a desktop implementation of that, you can get very sort of static sounding parameters when all the parameters are absolutely fixed, whereas when they're all slightly wiggling about due to noise, you can get it actually sounds better, I think. So that we can avoid tempting fate, but I think we can delete that question mark. That does seem to have fixed those glitches. Good. Okay, so we seem to have a working system. We've only got basically one output is just reflecting the input, one is just a test output. So the next thing to do then, I guess, is to, instead of having just this test code, we need to implement something slightly more substantial for all of the playback heads that are moving around. Okay, so I guess there's two stages to this. We have the movement of the heads, which we don't have at the moment. We've just got this fixed phase control. So we need to implement movement of those heads, and then we also need to implement the sort of the way in which they're moving, whether they're moving forwards or backwards or back and forth and so on and so forth. So, in fact, I don't know how this is done in the multi-mod. It's a bit of an implementation detail. I think the easiest way of doing things, in the same way that I was talking about before with the modular arithmetic being the easiest way to deal with these phases, I think the easiest thing to do is to, as we've done here, base everything off the recording phase. the phase offset here will now change with time. That's fine. We can have some values which increase with time. But then in terms of specifying whether it goes forwards or backwards or back and forth or steps or something like that, I think the thing to do is then apply a function to that phase, a bit like a kind of a wave folder or some function of that sort to that phase. So if we apply a kind of a wrapper or a rectifier, that would convert a sawtooth wave, which is what we've got at the moment, just playing straight through the wave in one direction, into a triangle wave, which would be effectively playing back and forth and so on. So we apply effectively a wave folder to the phase. I think that is, I don't know if that's how it's done in the multimod, but it seems like a reasonable way of doing it to me. So let's start, I guess, with the positions of each of the 4 tape heads. So because it's a phase, we'll use unsigned ints, and I'm going to have playback phase and 4 of those, and I guess I will start them. Oh, I never set record phase. So we'll start all of them in the same positions. And we then want the playback phases to shift as we play. So let's think, how and in particular where are we going to do this? I think we want to do it about here, because we want to deal with the playback stuff after we've done the recording, which is there. Okay, so we do everything 4 times, and really I think we're just going to have that the playback phase, we advance that by some phase advance, whatever that is. Now, one thing that the multimod website suggests is that there's a reset, which resets the positions of all of the playback heads to the position of the record head, and so we can do that. Let's put that for now at least on the switch. So that triggers once if the switch value is down. I'm not completely sure if that's going to work well with our sampling only 1 in 4 samples, but we'll check and see whether it does or doesn't. And then actually we also want there to be, we may as well use a pulse input to do the same thing, so we can, so that's how we do the same thing on pulse in 1 rising edge. So this should give us just a single sample, and this should be triggered once. Playback phase I is equal to record phase. Let's think. I actually think that is not quite right. Let's just have a look at computercard.h and see what. Yeah, okay, so that's not quite going to be right, because we could press the switch and it could trigger in one of 3 samples that are discarded. So I think what we need is up here, this is going to be one every sample, bool reset trigger, and that is going to be equal to I think what we want is bool reset trigger out here. Reset trigger is false. If all that lot, then reset trigger is true. Then if this happened, we catch that signal that was caught in any of those samples and we clear that flag again. Okay, so I think this should reset all of our playback phases back to our record phase when we either flip the switch down or we have a trigger into the input. But at the moment we don't know how those phases are actually going to change from the record speed, so we need some kind of I think this is where we need our speed knob to come in. So let's have a look. So we've got a phase knob and we've got a time knob. So maybe we'll probably add some CV in due course to these knob values, but for the moment we'll just leave them as they are. Now, okay, so we want a speed knob. Okay, oops. Rather than use an unsigned, I'm actually going to use a signed value here. I'm going to use the main knob, and the reason I want the main knob is because we actually do want quite a pronounced dead zone on this knob. As far as I can tell, the behavior of the multimod, there is a mode where if the speed is set to 12 o'clock, if that knob is at 12 o'clock, then it behaves in a rather different way, in that the playback heads are exactly a fixed time behind the recording head, and then you can control the phases, what those delays are. But it seems like that is a sort of two distinct modes, one in which those playback heads are going at exactly the same speed, and then one in which they're going at different speeds. But what that means is we need some way of having a bipolar control for the speed that goes through 0, but that 0 is a value we want to be able to hit exactly. And so what I'm going to do is have a signed speed knob that goes from minus 2048 to 2047 by doing that. And then if the value is greater than 100, then I'm going to subtract 100. Else, if it's less than minus 100, then I'm going to add 100. Otherwise, I'm going to set it to 0. I probably also want sort of fixed maximum and minimum limits. So at the moment, these are going to about, what is it? Well, it's 2048 plus, so minus 100, so it's going to be about 1948. So I think, so the ends of the knob travel are not, contrary to what early documentation suggested, the knob values in computer card are not guaranteed to reach the end points 0 and 4095. It appears on most systems as though they go to 4095, but they don't reach 0. But for this, I think I do want to sort of add dead zones at the ends as well to clamp the values to a known value. So if they're going up to 1948 as it is now, let's say 1900, because I don't think the I've seen the end of travel be more than 48 away from where it should be. So minus 1900. Okay, so that's putting some limits on. And then I want to give some kind of indication of when the main knob is set to 0, or when speed knob is set to 0, which is when the main knob is in between minus 100 and 100. And so let's use top right LED for that, LED 1, and turn it on if speed knob is set to 0. So okay, so let's see whether we actually can compile this. No, we can't, because I haven't yet done anything here. I'm going to set that to 0 for the time being, because for the moment I just want to test that that speed knob is working. So what we're hoping to see now is when I turn the knob. Yeah, okay, that looks good. When I turn the knob, when I get it at 12 o'clock, that top LED lights up. But it doesn't when I'm away from that. Okay, fine. So we've now got the speed knob, which can either be exactly 0 or it can be some position that isn't 0. But when it's exactly 0, ooh, I must be right on the edge of it there. Okay, it might even benefit from adding some hysteresis to that at some point. But that seems okay. So now that we've got that speed, we actually want to work out how fast we should move the playback heads through the sample through the phase, which goes from 0 to 232 each sample. And just for reference, the record head is moving through by an amount loop increment the phase increments by an amount loop increment every sample, because loop index goes by 1 each sample, so record phase goes up by loop increment each sample. And so we're going to need, I think, the playback phase. What we want to do, I think, is have those playback heads go at some range from like 1/4 of the speed of the record head to 4 times the speed of the record head when the knob is in the speed knob is on one edge. When it's at the other edge, I want to flip that round. I think this is what multimod does, roughly speaking, so that like the first output is the fastest when the knob is one way round, the last output is the fastest when the knob is the other way round, and so on and so forth. And sort of when the knob is in the middle, then all the outputs are going at the same speed, and that speed is the speed of the recording head. So we're going to need, this feels to me like something where we're going to need some kind of function to do this. And let's call that function PhaseAdvance. And I want to give that the index of the output from 0 to 3. I want to give it the speed knob value, and because the kind of unity speed value that we should give when speed knob is 0 is loop increment, I want to pass loop increment to that as well. Okay, so we now just need to write this function, and this function, I think, as well, is also going to use our power of 2 exponential function, because I want to have it, rather than a linear control on speed, I want to have it exponential, so it's 4 times speed or 1/4 speed at the two ends of the knob. So let's have a look at what this will be. I think it's actually just going to be a one-liner, but that one line might need a bit of thought. So I'm going to want a signed PhaseAdvance. Okay. There's a slight trickiness here. I'll type in the numbers here and then talk about what I am worrying about in a minute. type in the parameters rather. Okay, so do I want the PhaseAdvance to be... I don't think it matters actually here whether the PhaseAdvance is unsigned or signed. So the trick with how unsigned integers are actually integers modulus 2 to the 32 in this case, in principle doesn't always work with signed integers such as this integer, but on the RP2040 it does work, and so you can kind of treat them sort of slightly interchangeably. That we don't need to worry about the fact on the RP2040 and with this compiler we don't need to worry about the fact that overrunning the end of a 32-bit integer is undefined behavior. That just works. So what do we actually want to do? We want to set this to be some kind of exponential, and we basically want the PhaseAdvance rates to be loop increment times, well, I'll just write what I want it to be in mathematics first and then we'll see how to do that in code. We want it to be basically 2 to the speed knob times, okay, so I want the, when channel, well, I've got 4 channels, 0, 1, 2, 3. When channel 0 is slowing down, I want channel 3 to be speeding up, and I want channels 0 and 3 to do more than channels 1 and 2. So it's going to be something like speed knob times 2 times I minus 3, because 2 times I minus 3 takes values 3, 1, minus 1, minus 3, which is sort of how I want the channels to respond. Multiply that by speed knob, which is a bipolar signal, and then multiplying it by some constant, which I don't yet know what it is, to have an appropriate range of speed. So I said I think I wanted it to go from like 4 times to 1/4 or something like that, and that the value k is going to set that. So in fact I can see that we're going to have we're going to have some issues here, because we want this quantity, we want to have as much precision as possible. There's a question as to whether we can actually fit this into 32 bits or not. This quantity we want to have as much precision as possible, recalling that our 2 to the is going to have to be represented as the pow2 function, which we've written just up here, and that only outputs integers, so we only really get decent precision when we have very large powers of 2. So what I'm actually going to be wanting to do is output this to some, I don't know, I guess it's, fortunately I don't think this is going to be used for audio, so we don't need, I mean, we're very sensitive to speed changes when it turns into pitch, somewhat less so when it's CV. So we kind of want to multiply, given that this power of 2 has to be an integer, we want to deal with quite a high power of 2, let's say at least 2 to the 10, so we're talking about 1,000 or so, and then we want to divide the whole thing by 10 at the end. But then we are then in a position where this power of 2 depends quite what we set k to, but it's going to be at least a few thousand. And the question then is, how many bits do we want? How many bits is loop increment? So loop increment we said was 2 to the 32 divided by the loop size, and the maximum value, we said, let's get the calculator out, we said that the maximum value of that is going to be the minimum value of loop size. The minimum value of loop size is 12 kilohertz times, I think it was 62.5 milliseconds was the shortest loop. It's 750. Okay. So log 2 750 is 9.55, which means that loop increment is at most 22. It's 32 bits minus log 2 of loop size. It's about 22.5 bits. And our POW2 is at most, okay, well, so if we do go for, I think we want at least 2 to the 10 plus something to get enough precision in this. So it's 10 plus, I think we're going to have to decide what our K is going to be here. So this quantity is 3 at maximum. This quantity is 1900. And then we're going to multiply by K. 3 times 1900 times K, and then we divide by 496, which is how many steps per octave, and that gives us how many octaves does the fastest signal or the slowest signal differ from the input signal. Okay, so if we have just that is 1.39 octaves. I think that's not quite enough. So I'm going to set K as 2, which gives us 2.78 octaves, which is, that's plenty. Okay, so K is 2. So that's POW2 is at most 10 plus 1900 times 3 times 2 over 496 is it's just what we had before, plus 10 is 12.78 bits. Okay, and that does indeed exceed that exceeds the number of bits we've got available, because we've only got 31 bits available. If we want to fit it into that assigned integer, and actually we're at 34, 35 point something. Okay, so I think what we're going to do, what's the minimum value of loop size? It's 2 to 32 over 9600, which is still pretty big. 96,000. So 44,000. Okay, so I think... Right, so we're dealing with signals with a kind of precision of about 1 part in 1,000 here, because we've got 2 to the 10. If we divide loop increment by 2 to the 5, divides that by 32, that gives loop increment similar precision, and 5 bits is also what we need to get the sum of those down to below 31. So we want shift. So basically we're going to split this shifting down by a power of 10 into shifting loop increment down by a factor of 5 to start with, then shift the product down by another factor of 5. But in doing so, the product that we get should now fit into the number of bits that we have available. And this is going to be power 2. And we need to multiply everything by, okay, so it's going to be 10 times 496 plus speed knob times 2 times 2 times I minus 3. And all of that we want to shift down by 5 again. Okay. Not 100% sure about that, but we will see. So I think that should give us, let's just actually do a sanity check. If speed knob is 0, we want this loop increment to be, we want this phase advance to be just loop increment, because we want the read heads to be going at the same speed as the write head. So if speed knob is 0, that's just power 2 10 times 496, which gives us 2 to the 10. Oh good, yeah, so loop increment, shift down by 5, multiply by 2 to the 10, shift down by 5 again, gives us just loop increment out again, which is exactly what we wanted. Okay, so that looks right. Okay, so did we already put it in? We did already put it in. And because we are dealing with these phases as unsigned 32-bit ints, we don't need to worry about when the phase goes over the top of 2 to 32, it'll wrap automatically. It'll reset there. So actually I think we are ready to just get rid of these two lines. I'll comment them for now, and we can we can actually just put all 4 phases in. Let's create a sample position, or sort of so what are we doing here? We're sort of get the final position of output playback heads and convert into buffer positions. So those are our buffer positions. So what we want, the final phase, we want to be the playback phase, which is the thing that we have just been kind of incrementing to move around. But we also want the same phase control that we had before, though this time instead of phase knob times 524288 to go up to halfway, we want minus phase knob times I times half of 564 282144. And I think that should set the 4 phases. When the phase knob is at maximum, that means the 4 phases should now be spaced 90 degrees apart from each other. And so we should be able to tell that. Okay, so this is exactly the sort of step where we're gaining quite a lot in using these powers of these phases going all the way up to 2 to the 32, and then we want to the actual buffer position. We want to this is exactly this line of code. We just need to, instead of read phase, this is just now called final phase. Okay, hopefully we've got the compute to do 4 64-bit multipliers, but we will see. Okay, and so here now, rather than these audio outs, I'll comment those just in case this doesn't work and we need to go back. This should just be read buffer pos naught CV 0 1 2 3. Okay, let's make it, see if it builds. Yes, there's the bug. So let's Aha, right, good. Is this what I'm expecting? I'm not sure this is quite what I'm expecting, but we'll see. Right, well that could cause some problems. Let's see about that. Is that now completely smooth? So if I reset everything to 0 phase and I just move beyond, yeah, okay, that's now smooth. So I don't know why the scope signal keeps glitching like that, but the okay, now they are just going at slightly different speeds and going slightly in and out of phase with one another. Okay, that's interesting. So that wasn't very noticeable just from the speed of the little flashing loop size. So in fact, that could be part of the cause of some of the glitches we were getting in loop size. Is that smoother? That might be a bit smoother. This is turning to a really short loop and then a really, yeah, no, okay, you can still get quite glitchy signals. So I think it's still worth investigating the issue with kind of the extra tape that we're adding to the loop when we yeah, you do get little glitches there. Okay, well that's now looking pretty decent, I think. I mean, we may yet have more bugs to discover, but that's doing roughly what I would want it to, I think. Okay, so what next? I think the next thing is that we have some, at the moment, well, actually, what next? What I was going to say is we, at the moment, have these ramp waves, and what we want to do is, and that's indicating the playback heads moving forwards through the playback buffer. What we also want to do is have them go backwards through the buffer, and we want them to go back and forth and various other things that we can think of. But first I think maybe it makes sense to actually put some signals from the so that's nice. So this is sort of a couple of seconds loop time, and if I just give it a pulse, a single pulse on the slopes, so I'll just do a square wave pulse basically, is generating a whole range of different pulses, including a double pulse in one channel. So we're generating lots of shapes which look a bit like the thing I'm putting in. If I add a bit of slew rate on that and kind of toggle out a rhythm, you can see we're getting some pretty interesting signals, and in particular if I elongate the time difference, like a single, from just a few clicks on the switch, we're getting a whole range of interesting signals, sort of slowed up and speeded down versions of it on the four different channels. So that's quite promising for this being a kind of interesting generator of CV. Okay, let's have a look then at how we can cause these phases to run backwards or back and forth or anything like that. And I think the way I want to do that, as I said, is in this final phase here, I think I don't actually want to take just... What I want to do is take the phase that we get from these ramps and apply some kind of wave folder to it. So I think I want to apply a function called phasefunc, and phasefunc will be a function which takes a uint32t phase, and it's also going to take a type of function, because in the multimod we can toggle through things. So I'm going to have int function, which is the type of function. Going to start at 0, and there are a few examples. I think I'll start with just ramp and saw. So let's make an enum for that. With some integer values, and let's have this function accept. Okay. And then, so we want to be able to switch between ramp mode and saw mode, and in future some other types as well, once we've worked out how to do that. So I think then we've got this function which I anticipate being an index that we can increment through the different types of function. So I think what I want to do is, where we are dealing with the knobs, I think actually we want a similar thing to reset trigger. I think we want next function trigger. We have next function trigger is equal to false. If this is going to be, so we're already using toggling switch down for reset, so I'm going to have toggling switch up, switch val is equal to up, and switch changed, and we won't have a pulse input for this one because it's just a sort of front panel control. We want to here set next function trigger is equal to true, and then when we're collecting the knob values, knob and switch values, here I want to do if next function trigger function plus if function is big or equal to nfunc types, which was the last element in our enum, then function is equal to 0, and I also want to set next function trigger to be equal to 0. And the reason why so far I've used the LEDs on the on the right hand side of the LEDs is I want to, I think, use the 3 LEDs on the left hand side to display this function trigger. So what I'm going to do is, let's stick this right at the end next to our pulse LED. I'm going to make an array that tells me a bit pattern for these LEDs, because I think I'm going to want more than 3 functions in due course. So let's actually just define this func LEDs. That's going to be a bit pattern which displays some and how many do I want? Let's say 5. This is some poor coding here, because I'm defining 5 different LED patterns that I can think might be good but I have not tied that to the actual number of functions. So I want the top LED illuminated, I want the top and the middle, I want the middle, I want the middle and the bottom, and I want the bottom LED illuminated. So as we toggle through our ramp function, our saw function, and up to 3 more yet to be determined functions, we're going to display those LEDs. Let's just check that what's going on here. No matching call for phase func. Okay, that's because we've added a parameter here, but we haven't done anything with it. When we call the function in this, I'm going to need to, I think, cast this to func type, because I'm just casting an integer into an enum. Again, not good practice. Ooh, no return function statement in function returning non-void. Okay, that indeed is a problem, but here I just want to now return, let's just return phase for now. Did that reset properly? Yes, okay, good. So that is doing roughly the right thing. We can still control the speed. Okay, yeah. So nothing's really happening here because our phase func is just the identity function. It's just returning the phase. But what we want to do now is switch and case ramp. This is just doing exactly what we already have. Case saw, I want to case ramp, case saw, I want to return, I just want to make this go backwards, so I want to return minus phase. So here I'm really exploiting the wrapping on the unsigned integers. I think that should just make these go backwards. And I think that should be, in fact, yes, we can see on the, see already, particularly if I move the USB cable out of the way. It's not quite doing what I wanted. What's gone wrong with those LEDs? Oh, I'm going 0, 1, 2. Gosh, I need 0, 2, 4. No wonder. Okay, let's check. Okay. Okay, that now is finally, after some terrible coding, it's doing what I want. I don't know quite how visible that is on the it seems like I've got a big shadow. Let's just see how visible that is on the video feed. Oh yeah, you can just about see that the we're toggling between 2 light positions. Oh, and more importantly, on the scope, we're going from upwards ramps to downwards ramps. Okay, that's cool. So, if we again connect a slopes, and here I'm going to stick it into the top switch position. Let's try and lengthen that a little bit. just need to... What's going on here? Oh, I've turned the slopes too higher. Yeah, it's not completely straightforward to interpret what's going on here. Let's reset all of these phases. Oh yeah, okay, that makes sense. So when if I'm in this mode, I'm in normal mode and I've got a pulse which is decaying on all of the channels because that's exactly what the slopes is providing. If I switch mode, and so now I'm in the second mode, and do another, I'll wait for the loop to kind of empty itself out, and I do another quick blip and wait for a bit. Now I get it rising. Of course, there are some glitches as the playback heads go past the record head. They switch from an old recording to a new recording, or vice versa, and so we do sometimes get some glitches. But we're just reversing here what we are doing. Okay, so that's nice. So fundamentally, the principle of this, despite lots of bugs, is working. So what I now need to do is make some more function types. So let's have a think. So the next obvious one is triangle looping backwards and forwards. And there's various ways we could do this. But I think what is best is in the first half of the... So if value is less than 2 to the 31, return the value. Otherwise, return 2 to the 32 minus 1 minus the value, except I didn't call it value, I called it phase. Okay, so this is a triangle wave then. There's kind of two options we could have here. We could have the triangle playing twice as fast and going all the way up to the maximum value of 2 to 32, or we could have it only go halfway along the tape and go halfway back again. And I think probably the latter, which is what we've got here, is better, because then the speed of this is unchanged, and I think that's probably more important than playing through all of the buffer. Is playing through the buffer that we are playing through at the right speed. So good, so we've now got a new speed this whole thing up a little bit. Oh yeah, good. Okay, so we've got interesting. So maybe it is better this is a case where just outputting the phase, when I haven't got a jack plugged in here, we're just outputting literally the playhead phase. And here that's fine, but all of these signals are negative. And I think this is the correct thing to do for the playhead phase, because it's the thing that minimises the glitches as the playback heads cross over the record heads. I think they only do that once per cycle at the extremum of one of these triangle waves, at one of the changes over, which I think is about the best you can do. But for this normal signal, it would be better to have these centered around the around 0. That's something which we can maybe fix later. That requires a slight change in thought as to how we do this. That's not too bad though. It just means we have a slightly different phase function for whether we are using a normal signal or a recorded signal. Okay, so if triangle is doing that, we should also be able to do some kind of approximation to a sine wave, and then this will be the first one that that plays back data at something that is other than either a constant multiple of recording speed or the reverse of that. So it'll introduce changes in speed. So this isn't really a sine wave. Again, this is a case where there's sort of two options here. We could make a lookup table for sine, or we could just generate a parabolic approximation, and I think I'm going to do the latter for now at least. So parabolic approximation for sine is going to involve, I think, 4 regions. So the first region, the last region, the second region, and the third region. So the first region is the easiest. I want to return. So what do I want to do? Basically, I want this to be the smooth version of the triangle. The triangle goes from 0 to 2 to the 31, which is this number. That means this is 2 to the 30, and I want it to go from 0 to 2 to the 30, and I want it to be squared. So I need to shift the input values in by 15, because each phase coming in goes up to 2 to the 30. We shift both down by 2 to the 15, giving 2 to the 15 each. Square that, gives us back to 2 to the 30, which is where we want it to go to. Okay, and then it's the same deal for the last part of the cycle, except that rather than phase here, we want the 2 to 32 minus 1 minus the phase. So I'll explain, actually I'll just go, I'll explain what I'm doing here. We've got we want to make a triangle, a sine wave out of 4 segments, all of which are parabolas. Like that. That's kind of an approximation of a sine wave. This is 0, this is 2 to the 32, and we want the amplitude here to go from 0 to 2 to the 31. So the 2 sections I've just done are that section and that section, which is the same thing but just mirrored about 2 to the 32, and now it's going to be the same deal. I want to do this section and then this section as well, and those will equally just be mirrored, and hopefully those will all line up to a nice smooth sine wave. Let's see. So in this section we want it to be our maximum value minus, and then actually it's just the same as this, but where the 2 to the 32 is replaced by 2 to the 31. No, that's not. Is that right? Yes, that's right. And then for the remaining section, it's just, this is where phase is greater than 2 to the 31, so we just have to reverse that. Right. Well, I wouldn't bet that's right, but let's stick it in and see what happens. Question is, so that's our ramp, saw, triangle. Oh, it works. Okay, good. So that's the same as the triangle, but it's sort of smoothed out into a slightly rubbish sine wave. But I don't think I necessarily want to use a lookup table for that now, so that will do for now. Okay, so there are various other options on the multi-mod for this, which I'm not going to try and implement all of them. We've got one more left. I think there's something which is sort of advertised as a square wave or steps. I can't quite work out what it is, but one possibility is that we can add some kind of quantization to these functions, and so whereas we're just returning phase here for ramp, if we return phase but we chop out everything apart from the high order nibble, so that's going to only give me the phase in sort of discrete steps, that I think could be interesting as well. So that will be the first thing that's not just sort of directly playing through our recorded data, it'll be stepping through it. Let's just check how that works. Okay. There's our sign. Oh, cool. Okay, yeah, so that's basically doing our ramp waves, but is quantizing them to 16 steps, I guess, which is, that's cool. Right, and I guess we get exactly the same. If we don't, let's run this. Actually, no, I'm going to run a sine wave, an LFO sine wave into this. Okay, so we can see some glitches here where the sine wave that I'm putting in isn't exactly aligned with the buffer. Okay, there's all sorts of fun stuff we can do. Let's turn up some FM, why not? Well, that looks like a lot of fun. Let's actually I'm actually going to get some audio going. So I'm going to take maybe the last of these. So I'm going to unplug that and plug it into a stackable cable. So now actually I've got the blue signal and I can do something with it. I'm going to put that FM into a filter and hopefully hey, we can hear something. Okay, so this is just filter being used as an oscillator. Let's do that again, given we've got 4 signals. I'm going to take the pink one as well. And I'm just going to do exactly the same with the second filter. Okay. So this is just not quite sure what's happening at these glitches. Well, that's nice. Okay, so that seems to be doing something something interesting. So it looks like all of those modes are working. So what have we got left? So the card seems to be basically working, but there are some glitches in the output. So it's okay at the moment when we've got a constant loop time on the tape. But if I increase that loop time, we can see on the scope that we start to get glitches in the signal as I do so. And that, I'm pretty sure, is being caused by this issue we talked about before, where as we pull in more tape into the tape loop, we're pulling in data which hasn't been written to for some time, and so we're essentially getting random data there. And so what I want to do is see whether we can keep that tape that is just about to be pulled into the loop updated with data that can seamlessly merge into the tape loop. And the way I want to do that is by making sure that the record head actually records to that data too. And the way to think about this is, instead of just having a single loop of the tape loop going around and then all of the spare tape kind of trailing off into the distance, what I want to do is actually to wrap the tape loop around twice and then have the rest of it going off into the distance. And what that means is the record head will actually write to 2 points on the tape at once. It'll write to the position in the active loop that we're dealing with, but it will also write to a whole another length of the tape as we go along. And that means that as we increase the size of the loop, the tape that we'll be pulling into the loop will actually be already have stored on it exactly the data that would have been there if we had not increased the length of the loop. The data here will essentially duplicate the data that would have been recorded to from the tape anyway. And so I think this is going to help, probably not eliminate, but help the issue that we've got with the glitches there. And so what we need to be looking at is the code around here where we're actually recording onto the loop. So let's have a look. Let's make a section of code here. Okay, so this is a section now where we are recording the values to the buffer. And really, essentially, all we want to do here is, when we're writing buffer loop index is recorded value, essentially all we need to do is also write to the loop index plus the loop size. And that will mean that we write both to one position on the tape, but also to kind of the next loop of the tape as well. Now, I actually don't think this is going to work terribly well for two reasons. One, we need to make sure that this value is actually smaller than max loop size, but even if we do that, I think this is going to cause problems. But let's just do this anyway. So if loop index plus loop size is smaller than max loop size, then record to the buffer. We need to make sure that we are not going to overrun the end of the buffer. And let's write that to the tape. Write that to the card rather. Okay, so I'm just going to record some random data to the buffer, and then we'll let it settle down, and then we'll see what's going on. So I think this is actually going to cause just as many glitches, if not more so. Yeah, okay, different types of glitching, but definitely glitching nonetheless. And I think the problem here is that as we are, obviously loop index increases by 1 each sample, but all of these problems that we're having are when loop size is also increasing sample to sample, because I'm turning the loop size knob up. And so what's happening is that when we are writing the position, when we're writing the data to this buffer, we're not actually writing to every sample. So that is, when we're writing to this area of tape that's got sort of multiple colours in it, actually we're only writing to, you know, 1 in every 2 or 3 samples, and so we're missing data, and that data is still the old data that that is sort of random data that we don't want to be dealing with. And so what we need to do, I think, is instead of just recording a single sample here, I think we need to record multiple samples, keep a kind of track of where we last wrote to the buffer, and write a whole block's worth of samples to the recorded value. So that's going to need a bit more code. So I'm going to name this place that we want to write to extra recording index, because I think we'll use it again. So this is essentially the same code. If extra recording index is smaller than max loop size. Now, what we need to have stored here is what the last index was that we wrote to when we were doing this sort of extra recording, and we need to write to every sample between the last time and the present time. So I'm going to need a variable which is persistent between samples, so it needs to go up here, and I'll call this last extra recording index, and in the constructor we'll just set that to 0. And now we have 2 cases. If the place that we want to write to is bigger than the last time we did this, then what I want to do is actually do a loop. I want to start my loop at the last position. I want to go up to let's say up to, but not including, that will work, where we want to write to an increment, and then I want buffer I is equal to recorded val. So now, even if the successive positions that we're recording to are more than 1 sample apart, we'll just fill in all of the samples in between, and so we won't get this glitching. Now, let's just check that this isn't going to overrun. That's fine, because I is always less than extra recording index, and extra recording index is always less than max loop size, so that's fine. Now, we also will have the case where we are decreasing the loop size, and in this case a glitching isn't necessarily a problem, because we're not putting extra tape into the loop, but we still probably want to record to the tape. So let's just record 1 sample in this case. It may be actually that we don't need that line at all. That will need some more detailed testing. And then we've now got to, once we've done all this, we've got to set last extra recording index to be equal to extra recording index. That is, update the last value to the current one, ready for the next time we go through this. So, unfortunately, the scope trace itself is glitching pretty badly, but we'll just have to live with that. Doesn't like that. Recorded value. Okay. Let's see what this looks like. is I'm going to scrub buffer. Okay, that seems a bit, it's quite sort of discontinuous, but it's not too bad. Right, so now I've got quite a short loop time. That light's flashing pretty fast. Now if I increase this, okay, so it's not particularly smooth, but I think, yeah, we're free of those glitches where it's jumping for isolated samples to random values. It's not a particularly smooth transition, but I think that is just in the nature of the way that the we have relatively short sample sizes here, relatively short tape loop sizes, and so I think it's just as we go past the record head, we're getting discontinuities, but we're not getting glitches of the same sort. So that is fine. Now actually, let's just do a quick test on this. Is it any better or worse if I comment that out? I think it might actually work better if we don't even record anything to that loop if the tape is getting shorter. But let's see what this looks like. If there are more glitches, I'll come on the scope. No, it's hard to tell. I'll leave it in for the minute. I'm not sure that was any less. Let's just compare it again. I don't think there was a huge amount of difference, but yeah, it's possibly better like that. Don't completely understand whether that's helping or hindering, but it doesn't seem to be making a huge amount of difference in practice. So one thing to be aware of here is that we've now got a loop within our audio callback, and the length of that loop could potentially be quite long if there's a very rapid transition. And if we exceed the length of time that we're allowed to spend within a sample callback, the whole program will crash. So if I really why the scope's being so glitchy. If I really flick the knob as hard as I can, we're still not getting any. Still, the thing still isn't crashing. So this seems to be reasonably robust, but we will do a more stringent test of that shortly, because probably the next thing to implement is CV control over the various knobs. So we've got 3 knobs that we are processing. We've got the speed knob, we've got the loop size knob, and we've got the phase knob. So the phase knob is the easiest. What I want to do is just add a CV value to this. Now we have 3 free analog inputs on the computer, the audio in 2 and both the CV ins, and those quite nicely mirror the positions on the front panel of the main knob and knobs X and Y. And so for the phase knob, which is knob Y, the most obvious input to use for the CV is CV in 2, and here I'm going to now make this a signed integer because it's possible the CV values can create negative values in the way that the knob values can't. But I am going to limit what the phase knob can be to the value that the knob was limited to, that is 0 to 495. So if phase knob is less than 0, phase knob is equal to 0. If phase knob is greater than 495, phase knob is equal to 495. Okay, so we can now test that out. As you'll see, I've got a I've taken lots of the patch cables out, so we've now just got the the card running with a normal input, and we've got all 4 waves in sync. So as I turn the phase knob, these now go out of sync up to 90 degrees apart. I do wish the glitching would stop on the scope. And then back to normal again. And so really I just want to test whether that can be done by CV as well now. So if we restart that, and what I'm going to do is, I think I'll use one of the oscillators, the sine oscillator, to drive the CV input, because that's a full range bipolar signal. It's a little bit faster than I'd like, and I'm going to change this control to the middle. Okay, that's showing some slightly weird things, but let's just try and slow down that LFO for now. Ah, no, what's happening is I've got a lot of FM on it, that's why. I've got a problem. Okay, that's more like it. So the sine wave input, okay, that looks about right. So we're going from, what is wrong with this? I'm trying to refresh this. No, it clears up a bit. Sorry, but I am going to slow down the oscillator. So one little trick is that if we plug in the FM, turn it all the way up, and then 4 voltages, top right jack, top right button, and all the way over, I think, to the knob all the way over to the left hand side, I think produces negative voltage, and so that slows down the oscillator a bit. Let's just check, is that right? Yeah, that's right, it is slower like that. So that looks about right. We're changing the relative phase offset between those signals according to that low frequency oscillator, and that should look pretty much the same as what happens if we unplug that and just twist the knob smoothly, more or less. Okay, good. So we've got that working on the CV control working over the phase, and so we should be able to do something similar for the others. So the speed knob, I'll do something similar. The speed knob being the main knob, in fact this is going to be taking audio in too, that's the analog input that corresponds to the position, and that's fine. I'm already using assigned value, it's already centered around 0. There's a question as to whether we want the 0 on the knob to the dead zone in the middle of the knob to include or exclude the audio. I think we want it to exclude it, because with the normalization on, we're using the normalization probe. That means that when audio, there is no jack plugged in, audio in 2 will produce exactly 0. So by adding that signal on after we've produced this dead zone effect on the speed knob, that's not going to cause sort of slight creep or anything in the speed if we haven't got a signal patched in. And then in fact we've already got limits imposed on the speed knob, and so we don't need to produce new limits like we did up here. So that should automate the speed knob, I think. Let's give that a go. So while we do this, what I'm going to do is just see what it looks, remind myself what it looks like. Okay, so when we twist the knob, basically the faster and the slower oscillators shift from top to bottom. So hopefully when we make that and I need to save it first. Make that and copy it over. I'm going to patch up this oscillator. Patch up this LFO sine wave, and that's going to audio 2. I'm going to hope to see something similar. Excellent, I'm seeing something similar. That's just what I wanted. So it looks like we've got CV control over the speed as well. And finally, I'll leave it doing that. We want CV control over the loop time. And there's a question here as to, we probably do want to keep the hysteresis and apply the hysteresis to the sum of the knob and CV values. So let's make an integer which is time knob raw, which is just the sum of the associated knob x and CV in 1, which will be the value we use there. We'll now use that here in place of knob val x, because we want to deal with the sum of them. And I now need to go and check that time knob is signed, which isn't, it's unsigned. That's fine. And now the time knob, we don't want to go outside the range, so it will be the same deal as with the phase knob. We want the time knob to be restricted to the range that it always was, just by coming from a knob. Okay, seems fine. Calling these variables knob now seems a little confusing now. There's some of knob and CV, but that shouldn't affect things too much. Right, so now we need to just remind ourselves what. Okay, well now once we're in, now that we're in this mode without a jack in the input, so we're using a normal signal, it's relatively easy to see what a change to the timing looks like. So we know roughly what to expect from automating that with a CV, and I'll use my low frequency sine wave as before, and I'll set it about halfway. So we plug that now into CV in 1. Okay, there's a certain amount of glitchiness there, but I think that's just a inevitable result of automating the length of the tape loop. What I'm going to do is actually switch this over so that instead of using that sine wave, I'm going to use a somewhat slower slopes LFO. Okay, and this is now, let me turn that down. Okay, that's looking somewhat reasonable. There's a certain amount of glitchiness, but that's what you expect if you're pulling bits of tape in and out of the loop, automated in a CV-like way. So that's okay, but I have only been providing fairly slow CV signals to the loop, the length of the tape loop, and so if we remember down here, when we are doing a loop to write a whole load of values in the buffer for this extra recorded value on the tape in the kind of second loop round to stop the glitching from occurring. Remember, I was concerned here that if we increase the length of the tape loop suddenly, this is going to be quite a long loop, and that may exceed the time that we're allowed to take within the process sample function, and that may crash the code or make it do something weird. So if we go from a slow LFO here and we actually go to a square wave, that's the worst case scenario. So a square wave works okay. Gosh, this is very glitchy scope, but it's okay. But that's because we are looking at a very short buffer length. But if I increase the buffer length, so we're actually jumping quite large amounts, what's that going to do? Let's just drive this. Okay, yeah, drive it with a slightly higher frequency wave, and we've crashed the whole thing. Oh, in fact, you can see all sorts of random stuff is happening. The switch inputs are going haywire as well. So this means the whole system is sort of locked up, and it's got out of sync with its reading of the analog to digital converters for the audio and inputs and knobs and so on. So the only thing we can do now is reset that there. And I suspect if I, yeah, we can get it to crash again. Fine. So this is definitely, or there's certainly a problem, and I suspect this is the problem. And what we want to do here is make sure that the this loop never gets too long. And so what I'm going to do here is only loop up to a maximum number of values here. So and let's think how many values we're going to need. Let's go for 1500. So that is 1500 samples, which is just over 1/10 of a second of buffer. And hopefully that will be sufficient to avoid the glitching, which is why we wrote this bit of code in the first place, but also hopefully we can loop through 1500 buffer entries per sample without too much problem. So what I'm going to do is replace this with some loop end, which is just extra recording index. It's just what we had before. But if our start point plus the maximum number of samples we want to deal with, 1500, is less than loop end, then I want loop end to be equal to this. So this is going to mean, and then we loop to loop end here. So this is going to mean that we potentially are going to get glitches, but better, I think we'll only get glitches for really quite extreme variations of the knob, and better to get glitches than to have the whole thing crash. So let's see, it may be that 1500 is either too big and it still crashes, or it may be that it's too small and we still get glitches. So let's try the glitches first. Okay, yeah, so that doesn't seem to have introduced any further glitches. So it seems like 1500 is enough. Now let's see whether 1500 is too much. Right, if we again try and drive this with a square wave. Ah, excellent. Okay, that's driving it with an audio frequency square wave. Let's turn up the buffer. Is that going to work? Yeah, perfect. So it seems to be, or even with the sort of most aggressive input we can give it, which is an audio frequency square wave, and turning the buffer up, seems like it's pretty stable there. Good. So that seems to fix that. So with that, I think we are done, at least for version 1 of this card. So there's a few things that we could yet add. In particular, there's a whole feature in the multimod which we haven't got here. There's tempo sync on the time, the loop length input, which would be very useful, but I don't think I want to implement that quite yet, and so we'll leave it as it is, and I'll upload the code for this to GitHub.